Hello everyone, welcome to the video. So in this video, I'll be giving you a brief introduction to the finite element package Abaqus. And to do that, I'll be using a simple tensile test. So I'll start the program. When you open the Abaqus software, you can see a window like this. And if you go to File, you can see you can save your files here, and then in import you can import other files from other softwares like for example, you can draw your parts in AutoCAD and then import those complex geometries into Abaqus. And also you can export your Abaqus files, for example, to LSDyna and run it there as well. And if you go to view, and you can change your background colors if you want. You go to graphics options, and here you can see viewport background. You can change it to solid, and you can select any color from here. Select apply, then you can see the background is changed to white color. Okay, then here onto your left you can see your model tree. So here all the things that you have defined in your model will be visible, and you can easily go and edit it here as well. Here you can see the something called module, and when you click the module you can see a drop down list, and actually this is the sequence you should follow when you are modeling. So you can easily use this path or this sequence and easily start your modeling. So first we have part, and then the property module, and assembly, step, interaction, and so on. So using the part module, you can create your parts manually, and then using the property module, you can define your material properties and section properties as well, and you can use the other modules, so on. So I'll move on to the example. So before that, I need to tell you something regarding the unit system that is used in Abaqus. So if you have worked with some other finite element packages like SAP 2000, you may know that you can go and select the units that you are going to work with at the beginning. But that is not the case when you come to Abaqus. So there's no any place to you to go and select the units that you are going to work with, but there's a specific unit system that you need to follow from the beginning when you do the modeling. That means you need to follow this specific unit system, and you'll be extracting the results at the end from the same unit system. So you can see here in this slide, I have given you some unit systems that is used in Abaqus. Of course, SI is the most easier way to go, and you can see SI in millimeter unit system is what I have used in this example. So moving on to the example, as I said earlier, it is a simple tensile test, and you can see the geometry that we are going to model here. All the dimensions are given, and the thickness is 5 millimeters. So I'll go to the program, and I will start the modeling of the example that we have chosen. So I'll be first going to the part module, and here go to create part. Then you can change your part name. You'll enter part specimen, 3D deformable solid extrusion. We'll enter the approximate size as 300. Continue. Then you will be given a place to sketch your part and then generate it. So first of all, we'll draw a quarter of the specimen, and then we'll mirror it, and using that we'll generate the whole part. So I'll start with create lines. You go and just draw a vertical line, and then you can go and click add dimension, and then click on the line, and you can add the dimension here. So it is 90 in our case. Click enter. Now the new dimension is given, and you can go and draw a horizontal line now. Escape. You enter the dimension. It is 10. Enter. You go again and draw a vertical line here. Escape. Dimension. It is 25. Enter. Then you go to the other end now. Create line, horizontal line. Escape. Go to dimension. Click on the line. And enter 5. Go again, create line, start from the endpoint, draw a vertical line, escape, add dimension, click on the line, then add the dimension as 50. Okay. Now go to create arc and click on this point, the start point, as the start point. Then click on the other point as the end point. Now you can see an arc is being drawn here. So an arc is drawn now. Escape. Now you can see a quarter of the specimen is now is drawn now. Now we need to mirror this part, this quarter. So first we'll make these lines, we'll make this vertical line and this horizontal line as construction lines. So you go and select set as construction, and then go and select the line, then done. You can see now it is converted to a construction line. You do the same to this horizontal line. Go and select set as construction, select entities to set as construction geometry. Now you need to select the line, press done. Now both are converted to construction lines. Okay, now you go and mirror this part. You click and hold this feature, then you will open feature mirror. Select it. Select the type of mirror operation, copy. Then you asked with a mirror line. You can select this line as the mirror line. Select entities to mirror. You can select the whole part. Then done. Now you can see 1/2 of the specimen is now now it is drawn, right? Now you do the same again. You repeat the process. Select entities to mirror. Now it is done. Go and close it. You go and select mirror again. Type of mirror operation, copy. Pick the mirror line. Now you will select this horizontal line. Select entities to mirror. You go and select this whole part. Press done. Now you can see the whole part, the total specimen is now drawn. Okay, done. Then you go and press done here. Sketch the section for solid extrusion. Done. Now you are given with a place to enter the depth. That means your thickness. So you press here 5 millimeter thickness. Okay. Now you can see the part is generated under the module part. You can change your view from these options: XY, XZ, 3D option as well, and you can rotate using this option. You can select that one and then go and rotate. Okay, escape. Now the part is generated, and now we need to partition this face. To do that, so next what we are going to do is we are going to partition this face. Why we are going to do that is we need to partition this whole specimen as we are going to apply the boundary conditions, or we are going to fix this bottom end and we are going to apply the loading to this top end. To do that, we need to partition this part. So first we'll go and partition this face. You can go here, partition face, click it, then select the faces to partition. You go and click this face. Done. Select an edge or axis that will appear, vertical and on the right. So vertical and on the right should be this line. You go and select it. Now you are going to the sketching option. So you can go and easily sketch using create lines. You go and connect these points and draw the lines. Select create line, connect the points, escape. Create line, connect the points, escape. Now all the partitions has been done. Then click done. Now you can see the partitions are visible, but when you rotate it, you can see it is not in the other face. So what you need to do is we'll be partitioning the cell now. So you escape, then you go here, partition cell. You go and click and hold it. Then press partition cell, extrude or sweep edges. Now you are asked with the edge. You go and select this edge. Done. How do you want to sweep? Sweep along edge. Select an edge or define the sweep path. To define the path, you select this line. You can see the direction is now selected. You can it is visible now. Then you go and click create partition. Now you rotate it and see. You can see now the whole part is partitioned and can be selected separately. You see. Okay, now we are going to repeat the same process. Select the cells to partition. Select the lower part now. Okay, done. Select the edge. Done. Along edge. Select the direction. Create partition. Okay, now you see this is partitioned and this is also partitioned. So now we'll repeat the process again. Select, done. Select the edge. Done. Sweep along edge. Go ahead and select the direction. Create partition. Now it is done. Then the last step. Done. Select the edge. You need to sweep. Then done. Sweep along edge. Give the direction. Create partition. Now all the partitions are done. Okay. Close this. Now the part module is done. Then we'll move on to the property module. Okay. Here we can define the material properties and the section properties as well. So first we'll go to the material properties. Here you can see create material and material manager. So you go to material manager and go to create, and you can rename the material steel. Then go to general density, enter the mass density as 7.8 e to the power -9. Please note that now I am working with the selected unit system. You go to mechanical, elasticity, elastic. Enter the Young's modulus to 10,000. Poisson's ratio 0.3. Then you go to mechanical, plasticity, plastic. And here you need to enter the yield stress variation with the plastic strain. So you need to have the data set to enter here. I have it with me in the Excel sheet. So you go and copy and paste it here. Okay. I'll share these data sets with you so that you can easily start modeling this. Then you again go to mechanical, damage for ductile metals, then ductile damage. Then again you need these data set. Go here, take the data set, copy it, then paste it here. Sorry. Okay, now it is pasted. Then you go to sub options, damage evolution, and enter the displacement at failure as 0.02. Okay. Now the material properties are defined. Press OK. Now you can see the material steel is defined. Dismiss. Now we'll define the section properties next. You go here, section manager, create. We'll rename it section specimen, solid, homogeneous. Continue. Then you can see you can select the material which you defined earlier. Material steel. Press OK. Now you can see the section is defined now. Dismiss. Now we need to assign that defined section to this part. So you go and select assign section. Deselect this one and then select the regions to be assigned a section. You go and select the whole part. Done. Then they're asking what is the section. You only have section specimen, that is what we need. Select the required section. You can see the material also given here. Okay. Now you can see the color changes. That means the section is now assigned. Okay. Escape. Now the module property is done. Next you go to the assembly and create instance. So you have only one part in this example. So you can go and select it and apply. Cancel. Okay, now you can see in the assembly your part is visible. The specimen is visible now. Then we'll create a datum point here. What we are going to do is we are going to create a reference point and we are going to couple this whole top end to that reference point and we are going to give the loading to that reference point. That is what we are going to do here. To do that, we need to create the reference point and to do that first we need to create a datum point. Okay, for that you go and click here, create datum point. So you go and click and hold it, then you will be given create datum point midway between 2 points. Select it and then select the first point, the middle point, and the second middle point here. And you can see a datum point is now generated. So next we again go click and hold this, then you go and select create datum point offset from point, then you go and select this create a datum point, and you are going to offset this one from 10 millimeters in y direction. So you go and edit this 0 10 0, enter. Now you can see this point has gone up exactly 10 millimeters. Okay, now we are going to define a reference point. You go and select tools, reference point, select a point to act as a reference point. You go and select this datum point. Now you can see a reference point is now generated, RP1. Then we will create a set from that reference point. You go and select tools, set, create. You say set RP, reference point, continue, select the geometry for the set. You go and select RP1, done. Now you can see the set RP has been created, one reference point. Now reference point is all done. The module assembly is finished now, completed. Now we'll go to the module step. So first we need to create a step. For that, go to the step manager. You can see here there's a step by default, the initial step. It is there by default, but you need to define the loading step. For that, you go and click create. Step 1. So you need to select the corresponding procedure type. In this case, we'll use dynamic explicit. Go and select it. Continue. And the time period is given as 1. That means 1 second. You go to mass scaling. Select use scaling definitions below and create. Here under mass scaling we are going to do the mass scaling in this model. So you go and select edit mass scaling, then select whole model and deselect this and select this one and deselect this and input the target time increment as 1 e to the power minus 4. Okay. Now the mass scaling is done and the step is defined. Okay. You can see now the loading step is defined. Dismiss. Next we'll define the history outputs and the field outputs. That means we need to request what we need in our results. at this step module. So we need to define that to the program. So you go to here, history output manager, select it, and you go and delete this one, yes, and then create one. History output 1, continue, and in this window you go to the domain set. Now you can see the created set is visible here, set RP. Then select displacement. What we need is displacement in Y direction, that means U2. Go and select it, U2 is selected. Then we need the reaction forces. Go and select it here, forces, RF, reaction force in Y direction, that means RF2. Now both are selected and press OK. Now the history output request is defined now. Dismiss. You go to field output request manager now. Then edit. Here you go to state, field user time. Then click status and OK. Dismiss. Now the step module is done. Next we'll go to the interaction. You can see here the next step. The next module is interaction. You go here, and here we'll be coupling this reference point with this top end. So to do that, you go to create constraint and select coupling, continue. Select the constraint control point, select this reference point, done. Select the constraint region type, go with surface, then you need to select this whole top end. You can see the whole top end is selected now. Escape, done. So we are going to couple this top end with the reference point. That means all the translations and the rotations are restrained. Okay. You can see the top end is coupled to this reference point. Okay. Now the interaction module is done. We'll go to the load module now. Go and select it. So here we'll define the boundary conditions. That means we are going to fix this bottom end now. To do that, you go here, create boundary condition, select it, and you need to change the step to initial. Select symmetry, anti-symmetry, encastle. Continue. So next you need to change the selection type to cells. Then only you can select this bottom end as a cell. select regions for the boundary condition. Now you can go and see. Now you can select the bottom end. Done. And go and tick encast. That means fix boundary condition. You can see U1, U2, U3, UR1, UR2, UR3. That means displacement in all direction and rotation in all direction, all are constrained, means 0. In other words, it is fixed. Okay. You can see the boundary condition is applied. Okay. Then we'll give the loading condition for this reference point. So you go. So how we are going to define this loading condition is we are going to define it as a displacement. So we say the displacement of this reference point starts with 0 and it goes on and ends in 10 millimeters vertically upwards. That means in y direction. So we are going to define that. Go to create boundary condition. We see 2. Now we are going with displacement rotation. Continue. And to select the region, now we are with selection type cells. So first you need to convert it to all, and then select RP1. Done. And you constrain all these U1, U3, UR1, UR2, UR3. So only U2 is released now. Click OK. You can see now it is defined, but you need to go again and you need to modify this boundary condition. Select it and edit. Now you again go and select U2. Sorry. You go and select propagated under BC2 and edit. Now you can see all these values are 0, but what we need to add here is 10 millimeters because our maximum is 10 millimeters. So you enter 10 here, and we need to define how it is changing from 0 to 10. So to do that, we will define an amplitude. So at the moment we haven't defined any, so you go and click here, create amplitude. Select tabular, continue. So we need to enter the data set, how it is changing with time. So I have it here, the data set. Go and copy it and then paste it here. Now it is inserted here. Click OK. Now you can see the defined amplitude is visible here. You can click and select it. OK. You can see the displacement direction is vertically upwards. Dismiss. Now the load module is also done. Next we have the mesh module. That means we need to mesh the whole part. We are going to define it here. So you can directly go and auto mesh this one using this feature seed part instance. dependent part instances cannot be edited or assigned mesh attributes. So these are dependent paths, so that you need to select part. That means you need to mesh these part wise. So you select the part, we have only one part, then you go and select seed. Then you can apply a global size. We'll enter 3 and apply. You can see the seeding is done now. So these are the points that will cross the meshing lines. Okay. Then you go and click mesh part. Okay, to mesh the part. Yes. Now you can see the whole part is meshed now. Okay. Now the meshing is done, but we need to define the element type. So you go and select assign element type, select the region, whole part, and here you need to select explicit. We are going with dynamic explicit, and the 8 node linear brick element, that means C3D8R, and you need to go down in this list and you need to select yes for element deletion. Okay. Now the element types are also assigned now. Now all the modeling parts are done. We need to go and create a job now. So you go here, job manager, create one, job 1, model 1, continue, and you see here in the submission you need the full analysis, but you can go to the parallelization and you can use multiple processors. You can increase the number of cores, and that will reduce the computational time of your model. So you go here, click OK. Now the job is created now. Then you go and submit it. Okay. Now you can see the program is trying to solve the model. Status is submitted. Now you can see the model is solved, or it is completed now. You can go and click the monitor and you can see all the steps, how it is solved. And there are no errors. You can see it is completed. So dismiss, and you can view your results from here. Go and click results. Then it will be opened in the module visualization. Here is where you can see and view, extract your results. So you can start the animation, animate time history. So you can see how it is working now. You can see the fracture, And if you closely see, you can see the necking as well. So the behavior is modeled, and you can plot your von Misers or any type of stressors. Here it is von Misers. You can change it from here. S means stressors. Now it is Misers. That means von Misers. You can plot any of these: maximum principal, mid principal, minimum principal, Fresca, pressure, third invariant, S11, S22, and likewise. You plot S22 here. Can select it. You see the stress variation is plotted as well. How the stress varies. If you want to slow it down, the animation, you go here, animation options. You can reduce the frame rate and apply. Now you can see it is slowed down. Cancel. So this is if you want to see the deform shape, final deform shape, go here. You can select any frame that you want. Frame by frame you can select. If you want to go to the final step, you can go here and you can just view it. Then if you want to plot any variation with XY coordinates using this model, you go here, create XY data, ODB history output, continue. Then you can see so here you can see the entities that we defined earlier in the history output request. It is now generated here in the results. So you can go and plot the reaction force if you want directly. Go and plot it. You can see here. You can see how the reaction force, history, force with time, or else you can go and plot the spatial displacement u2. You can see it is varying from 0 to 10, which we define 0 millimeters to 10 millimeters. Okay. Then you need to save these outputs. You go and select one, save as, go with as is. You don't need to plot it. Okay. Then do the same for spatial displacement, save as is. Okay. Now I'll show you how to combine these outputs and generate another separate plots that you need to extract through these results. So you go and select XY data manager, create XY data, then operate on XY data, continue. Then you can see since we saved them, RF2 and U2 are visible here. Then we are going to combine these two. That means we are going to plot the load displacement curve now. So that means we need to combine these two expressions. So you go here and go down. You can see combine xx. Select it. Now it is there. Then you go to u2 and select it. Add to expression. Now it is here u2. Then go to rf2 and add to expression. Okay. Then you can plot the expression. Now you can see the load versus displacement or force displacement diagram is now plotted. So likewise, you can uh, use any of your results and combine them, and you can do anything with them, and you can plot the variations that you want. Okay, so that is the end of the tensile test example. Hope you find this interesting and you got something out of it. So if you find this valuable and knowledgeable, you can like this video and share and subscribe to my channel as well. So hope to see you in the next video.